Hello everyone, my name is Payman and today I'm going to talk about memrestive data clustering. Clustering techniques are increasingly used by various fields of science and engineering for important applications such as self-driving cars, robotics, World Wide Web, economics, machine learning, and also precision medicine. But what is a data clustering? The process of segregating a large number of data points based on data similarities is called data clustering. For example, suppose that we have several data points here. By applying clustering according to characteristics found in the data points that are similar to each other are grouped in the same cluster. For example, here we can have a red cluster, a blue cluster, and also a green cluster. What is a K-median data clustering? K-median data clustering is an important example of the K-clustering family. It represents each partition with the median of all members of the same cluster. The advantage of the median over mean is that median is more robust to the outliers than arithmetic mean. For example, here for the 1, 2, 3, 4, 2, 3, 4, 2, 5, 5, and also 1000 as an outlier, the mean is 93.72 while the median is 3, which shows that how much mean is more susceptible to outlier while the median isn't. K-medians, as a result, provides better clustering quality for the numerous applications and hence is a good fit for unsupervised learning tasks. So, how we can compute the median? The median is the middle point of the sorted data. For example, for the given data, the median is 6. How to compute the median? This has been an interesting question for designers. We can find two important approaches for computing in the literature. The most common approach is based on sorting, which needs higher complexity than computing the mean. Another solution is rank order filters from the signal processing domain. For example, bit serial rank order filtering or ROF, which is even more complex. Let's see how the bit serial median algorithm works. Let's assume that we have 5 data points including A, B, C, D, and E with values 5, 11, 7, 3, and 8. Every number is represented in a binary format within a single row, starting from the most significant bit toward less significant bit. The algorithm performs a vertical computation followed by a horizontal bit propagation repeatedly to find the median bits. First, compute the majority vote for a bit position. The result of the majority function is used to determine a bit of the final result and also to identify the minority bit within a selected column. For example, here for the first column the majority is 0 and the minority is 1. In the next step, the minority bits are used to replace all of the bits on the right hand side. For example, here the 1 is propagated from MSB to LSB. The same procedure happens for all of the remaining columns. Finally, the result appears at the bottom, which is 3 in this example. What is the challenges of bit serial median filter? Challenges of bit serial median is excessive data movement. All of the operations are performed at the bit level. This technique may require even more data movement between the functional unit and also memory in conventional hardware architecture that degrades the performance and also increase the energy consumption. So, what can we do to mitigate these problems? Our novel proposal is a memory-centric hardware accelerator for in-situ k-median clustering based on bit serial median rank order filters or ROF and recently developed resistive RAM or RRAM technology. For example, recently clustering has seen wide use in medical research such as cancer diagnosis. In the case of diseases such as cancer, the gene of normal body cells undergo multiple mutations to evolve cancerous cell. As shown here, this anomaly is now possible to be detected through a procedure called gene expression analysis that requires clustering a large number of gene samples. For every computation task, 3 steps are followed. First, the module is configured by the software for solving a clustering problem. Next, the in-situ computation here will be triggered after transferring the data from the main memory to the accelerator chips. Finally, the processor will be notified by the accelerator to access the result. We will go through the details of each proposed components. Resistive memories are non-volatiles, almost free of leakage power, with high speed switching, and also they are denser than DRAM technology. This figure shows an example topology for one transistor, one memristor, or 1T1R memory cell comprising an access transistor and also a resistive storage element. The cell's content is read or written by applying an appropriate voltage across the memrestive element. During write, we can apply a high voltage, for example, a set or reset voltage that change the state of the RRAM from 0 to 1 or vice versa. This can be accomplished by activating an access device using a word line and also applying the required read or write voltage across the bit line and also bit line bar. During read, again we apply the voltage and measure the current. However, this voltage level shouldn't change the state of the RRAM, so it shouldn't be beyond or even close to set or reset voltage levels. The key idea behind the proposed in-situ data clustering with RRAM cell is shown in the consecutive three slides. This figure shows how the majority function can be computed through parallel memristive cell connected to a single bit line. Assuming that each memory cell employs its high and low resistance state, for example R high and R low, to represent 1 and also 0 respectively. The number of ones determines the amount of current or I flowing through the bit line. By measuring this current and comparing it with a threshold, one can determine whether the number of ones is greater than the half of the bits or not, and thereby computing the majority vote. This capability is leveraged to realize the vertical computation step in bit serial median filtering algorithm. This figure shows an analog bit counter designed for the proposed accelerator to compute the majority vote per every column of data arrays. Notice that the bit counter unit is proposed to replace the conventional sense amplifier circuit in RRAM arrays. In addition to reading individual cells, the proposed analog bit counter is able to quantize the total amount of the current pulled by the bit line into multiple digital values. This slide shows how the proposed circuit work for performing in-situ bit comparison using two serially connected RRAM cells that formed a voltage divider network. Depending upon the input voltage, for example V0 and V1, and also the state of the R-RAM cells are high and are low of R0 and R1, the voltage divider produces an output V out that varies between almost V or 0. Please pay attention that when one of the input values is high, another input values is low. As a result, the logical function implemented by this circuit can be summarized in this table. As you can see in the table, the output value represents the result of a binary XNOR on V and R. This novel functionality is used in the bit serial median filter for finding the minority bits, as well as in the K-median algorithm for searching and also selecting all the members of dynamically formed cluster prior to finding a new centroid. This figure shows the circuit, an example physical layout for the proposed memory cell capable of 1. Serving ordinary read and write here, and also performing in situ XNOR between the cell, for example R value, and also external input, for example the majority value, and propagating the minority bits to its adjacent cell. 3 word lines and 4 bit lines are provided to perform read, write, and compute operations on the cell. Every memresitive element in the proposed cell can be read or written through a set of 3 bit lines and word lines, which makes it possible to use the proposed cell as 4 individual 1T1R memory cells to store data. So let's look at the computing mechanism. Computing bit serial median requires multiple steps, each of which involves activating the cell using bit lines and word lines. As seen, P and I are initialized to determine if the current cell should be included in computation. This is necessary to ensure that the irrelevant data points are not included in computing the median values. As shown in the table, only one or none of the column in every row contributes to the bitline current. First, none of the cells are selected if Pi equals to 0, 0. Second, column Bi is included in the majority root computation if Pi equals to 0, 1. And third, column Bi minus 1 contributes to the majority word computation if Pi equals to 1, 0. By measuring the current driven through the compute bitline C and also comparing it with the threshold, the majority can be computed. This figure shows how the new value for P and I are determined. The newly computed majority word is applied to M and is negative to M bar. E is connected to VDD, activating the access transistor, and an XNOR part of the cell here generates an output which is M XNOR R on the word line I. On a 1 to 0 transition, first I is set to 0 and will remain in the same until the end of computation. And second, P is set to 1 only if M equals to 1. Let's have a closer look to this adjacent cell. As shown here, 2 paths are possible for flowing current between VDD and also ground. One path, which is number 1 here, is through column Bi that determines the amount of current driven from the bit line based on the content of data bit. And second is The path includes the memresitive element of the previous column or bi-1, which is always set to R low to determine the amount of the current pulled from the compute bit line in the case of bit propagation. Notice that P and I are used to enable the current path. One difficulty in realizing in situ bit serial median computation is propagation the minority bit within each row that results in forming line chains of cell and thereby impacting the area, delay, and also power dissipation. The proposed cell architecture avoids forming line chains by allowing only ones to be propagated from bi-1 to bi. Notice that 1 and 0 are represented with the low and high resistance state respectively. Because of the significant difference between the high and low resistance state in RAM, for example, R high to R low is in the order of 10 to the power of the 5, the current contributed to the bit line by those memrestive cells in high resistance state can be omitted. This optimization is considered by dedicating a low memrestive element in bi-1, which is included in current summation only if P is high. After computing the majority vote in the current column or bi, P and I are recomputed here to processing the next column. For example, bi plus 1. Let's now put together the cell in the array and perform the operations at the array level. We need two arrays for labels and also data points connected to each other through a row selector. Number 1. Initializing centroids. Every k-median clustering task begins with randomly initializing the centroids, which are maintained by the bank controller in local buffer. Second, the next is forming new clusters. The bank controller forms new partition by reading the data points from the data subarrays and comparing them with the centroids. Third, the index of the closest centroids to every data point is used as the new cluster label for that data and will be written to the label array. This is accomplished through a set of serial comparators in the bank controller. As the data points are read out, the serial comparator determines the index of the closest centroids to the data. The centroids of every cluster must be recomputed by applying the bit serial median algorithm to all the elements of every cluster. This requires a bank controller to keep track of the cluster members at all times. Next, the label array uses the same structure as the data arrays to carry out the required bookkeeping for all of the data points. At the beginning of every median computation, the label arrays are searched for matching entries using the cluster labels one after another. The fifth stage, the outcome of every search operation is the matching lines in the label subarrays connected to a row selector unit to determine the I and P values for the data arrays. Next, the medians bit are computed by iteratively performing the vertical majority vote computation followed by a horizontal minority bit propagation. And finally, as being serially computed, the medians bit are streamed to the bank controller for updating the centroids. This process will end after a certain number of iterations defined by software or when all of the newly computed centroids are the same as the old ones. For example, when the convergence happens. So, what is the system architecture? The proposed Harvard accelerator employs a hierarchical organization of data arrays, banks, and chips to form a memory module capable of solving clustering problems varying in size. The accelerator module receives data and commands from the CPU over an off-chip memory bus. Then software initiates every clustering job by writing the configuration parameters into the chip register. For example, size and the number of iteration. Only a small fraction of the memory address space, for example 1 kilobyte, is dedicated to the chip register, through which all of the configuration parameters, status flags, and also data points are transferred between the software and also hardware accelerator. Regardless of the data size, one chip register is dedicated to transfer the data to the accelerator. The chip controller receives the data to be clustered word by word and distribute them into data arrays across multiple accelerator banks. Similarly, a data output port is employed to collect the results of data clustering from the accelerator. Also, we have an energy-efficient reduction tree that is designed to retrieve the practical data from the local analog bit counter. Okay, let's look at the operation in the reduction tree. A reconfigurable reduction tree is used inside every bank to interconnect the data arrays and also chip controller. The proposed tree is capable of selectively merging the partial counts from data arrays into a single count value. For example, this slide shows the proposed reduction unit employed to realize 9 possible ways of reading data points from the children arrays A, B, C, and also D. All of the reduction units at every node of the tree can be connected, for example, to a shared 4-bit mode register. The nodes are programmed to appropriate operational modes prior to solving clustering problems. These nodes at the same tree level are programmed to the same mode values, for example M0. It is now possible to read the individual arrays that are used for serving ordinary read requests, or to read the sum of the values provided by every 2 or 4 adjacent arrays, which is used for computing the count value. This flexibility is essential to achieve significant energy efficiency in computing those problems that partially occupy the accelerator banks. In the proposed data clustering platform, software is responsible for computing the most bits for a given problem size. These most bits are then streamed into the accelerator during the chip initialization phase. How the proposed accelerator handle floating point numbers? We observe that a 64-bit fixed point format for the evaluated applications and dataset achieves virtually the same result obtained with the double precision IEEE floating point format. Nevertheless, for sensitive application, the proposed accelerator is flexible enough to compute the medians of the wider bit representation by increasing the number of vertical majority vote computation and also applying the minimal changes to the control logic. These slides here shows an example of floating point to the fixed point conversion. As you can see, the input floating point data are scaled by a factor of 2 to power of the 3 and then are converted to a fixed point data. We now apply an ROF to compute the median of the fixed point data. How about negative numbers? The proposed accelerator addresses the negative numbers concerned by representing the input dataset in bias notation. For example, a bias of 2 power of the n is added to all of the negative and positive elements. For example, here you can see we have several integer data points. A bias of 2 to power of the 3 is added to each of the data points to make them positive, and the median is then computed by an applying ROF algorithm. Here we summarize the key performance results for the proposed architecture. We compare the results of the CPU, processing in memory or PIM, and also the proposed accelerator. PIM places the functional unit next to the data arrays on memory dies to alleviate the significant cost of data movement between the processor and also memory in every iteration of the algorithm. The impact of increase in number of clusters on the overall system energy and execution time of the CPU, PIM, and also the proposed accelerator is shown in this plot. As you can see, the proposed in situ accelerator achieves between 22 until 290k times and also between 8 to 81 times better energy delay products compared with the CPU and also PIM baselines respectively. This was a summary of our proposed memrestive data clustering.